Hi everyone, and welcome to More Than a Slice, which is a webinar discussing how you can move beyond simple slice-based calculations by using LimitState GEO. My name is Tom Pritchard, I'm a Principal Engineer here at LimitState, and I'm the host for today's webinar. We're scheduled to run for about 30 minutes with some time at the end for a Q&A. If you do have a question at any point, please do feel free to enter it into the webinar interface, and we'll try to get around to as many as we can at the end. So, without further ado, I'd like to pass you on to our speaker for today, who is Dr. Colin Smith.
Okay, thank you very much, Tom. So welcome to this, our second LimitState webinar of 2021 and our first LimitState GEO webinar. So today we'll be looking at slope stability. And what we'll do is we'll take a brief overview of current analysis methods and then take a look at the underlying technology of LimitState GEO and a practical example. So to this end, I'll be using the software directly to illustrate the points, but as this is a short presentation, the main aim is just to give you a flavour of what the software can do, and there won't be time to get into the details of the software functionality. However, as Tom said, there'll be time at the end for questions. Now, just to introduce slope stability problems, often it can be quite a complex area. Often we're dealing with complex stratigraphies and surface profiles. We may have spread loadings and very localized loadings. We may have complex water conditions, potentially pre-existing slip surfaces or weak layers in our soil. And if we're trying to improve slope stability, we may well have reinforcing elements such as piles, walls, soil nails, and geotextiles. And obviously, geotechnical engineers require ways to analyze such problems while adequately capturing the core mechanics. So common technology currently in use is the method of slices, and that was developed to address the challenge of analyzing slopes in a way that was amenable to hand calculations. So most of the development of this was done back in the 1950s and was a very good method at the time for allowing hand calculations just to get engineers to give them a handle on what the problem was and get a decent estimate of stability. This has now become a standard basis of many software solutions, and it has been enhanced. Various additions have been made to the method. However, at its core, the method does presuppose a slip circle failure mode or something similar, and has to make some assumptions about interslice interactions, and that can skew the solution into certain directions. So the question is, do we still have to stick with that type of approach, or with modern computing power, can we rapidly search all possible failure modes, not just slip circles, while satisfying the mechanics of yield? And the answer is yes. What we can do is use limit analysis. Now, limit analysis is a rigorous method of analysis based on plasticity theory. It's been used for decades by geotechnical engineers to analyze collapse states for slopes, retaining walls, foundations, etc. And the key assumptions are that the soil behaves as an ideal plastic material, and we use more Coulomb or Tresca yield surfaces, which are familiar to geotechnical engineers as the yield surfaces we tend to use for frictional materials like sands, gravels, and Tresca for clays. And a typical analysis method that comes up in textbooks are Coulomb wedge type analysis and slip circle analysis, shown in the diagrams on the right. And they encompass the core functionality of limit analysis. And if you take that method to its limit, you can then explore many, many different failure modes. But with the particular method, there's no need to specify a solution type or interslice forces or entry-exit points. It has the potential to identify any shape of slip surface. As I've said, traditionally in textbooks, you tend to see these as very simple solutions with one sliding surface, or perhaps one or two sliding wedges in a Coulomb wedge analysis, but can we go further than that? And the answer is yes, we can use what's known as discontinuity layout optimization to take that limit analysis technique to its limit, if you like. So this is a systematic, automated method of identifying the critical slipline pattern using limit analysis, published back in 2007 in the Proceedings of the Royal Society, and essentially poses a problem as a large but simple linear optimization problem. And it makes use of very, very advanced, very powerful modern optimizers that run on desktop computers to analyze these large problems and identify the critical slipline pattern. And what I'll do is just go through briefly the process. So here we have a domain with supports to the left and the base and a little load on the surface. Instead of populating the domain with elements, as in the finite element approach, we populate it with nodes. And we connect every node to every other node with a potential slip surface. So here we've got 12 nodes. We have 12 times 11 over 2, 66 connections. And we then use optimization to pick out the set of connections that form a collapse mechanism that essentially dissipates the least energy. That's your critical collapse mechanism. And out of those 66 lines, we get 6 lines which give us this collapse mechanism. So if you like, this is solving a surface load against a vertical cut in a very simple way with only 12 nodes. But we can use far more than 12 nodes. We can use 1,000 nodes or 10,000 nodes and get much richer set of potential slip lines, and that is essentially how software works. And so it's not restricted to any particular pattern of failure. It can connect these slip lines up in any pattern that it likes to give us the critical mechanism. So that's a very brief overview of the technology behind the LimitState GEO software, and we'll look now at a simple slope example. So this is essentially a 2-in-1 slope with 2 layers of soil. The top layer of soil, we've got a C-10, a phi-30. Bottom layer of soil, C-5, phi-25. And if that is solved using method of slices, we get the solutions down here. So all around about 1.74-ish for the different methods. And method of slices is generally going to be trying many different slip circles to find the optimal one, and the one here is pretty close to where we are. So we'll look at that in the LimitState GEO software. How can we solve that? So I'm just going to drag across a window with, I've already opened that file. So this is our LimitState GEO interface. And the model has been pre-built. You can draw models, you can import models from DXF files and so on. There are many different ways of constructing a model, but to save time here, I'm simply got a pre-prepared one. So before we start solving the problem and looking at the analysis, just briefly go over the layout of the software. So down the left, we tend to have buttons related to controlling the geometry, the view of the problem. We've got the top menu bar, and those are generally to do with the solution method. And then on the right, we have this thing called a property editor and a geometry editor. So anything we click on in the problem window, its properties will appear on the right. So if I click on this block of soil here, you can see it will give me the geometry down here in coordinates, and I can edit those if I wish. We'll look at that later on. And it gives me properties of this solid, and one of the important things is that it contains a material called soil A. And if I click on that, I can see its properties. It's got this C-10, phi-30. Various other properties we don't have time to look at. You can also see on the left we've got what's called a Materials Explorer. Soil A also appears there, as does soil B, and you can see that's got the properties 5 and 25, and soil B is this lower block of soil. Now to solve the problem, I just click this button and it will identify the critical failure mechanism. So I'll click solve, and it's doing what's called a factor strength solution. So what it's trying to do is find what is the factor on the strength of the soil that I've defined that would lead to collapse. So currently the problem is stable with the strength of soil that it has, and what the software is telling me is this is the critical failure mechanism, and this value down here, 1.773, is the value that is required to cause the soil to collapse. And if I click on that, it tells me a little bit more. It says, here are your initial soil properties, characteristic values, so we're using the Eurocode terminology, 10 and 30 for soil A, 5 and 25 for soil B. The design value, we're not employing any partial factors in this analysis, so they're the same. And to get collapse, it's saying you've got to divide all these numbers by 1.77, and these are at the actual strengths required to see collapse. And that 1.77 is pretty close to the method of slices results we saw early on. In fact, I'm running this just for speed on quite a coarse setting of nodes. I can show you what that looks like. So I'm not using that many nodes in this problem just for convenience, but if we run with more nodes, we will get a more precise answer. That is essentially the core use of the software. It's very simple to get that solution. You don't have to preset entry exit points, choose a solution type. It just goes straight there. But you've also got the flexibility to experiment. So, for example, I can change the gradient of the slope just by dragging and dropping and resolve, and it will give me a different failure mechanism. And you can see this time it's just, I think it will end up involving the base soil. And we get a higher factor of safety, which is what we would expect with a shallower slope. Equally, if I click undo, put the geometry back to where it was, if I wanted to stabilize the slope, I might, for example, construct a berm, so I can add a polygon here. And put in a different soil. I'm going to, there's some predefined materials here just for convenience. I'm going to put a dense sand there and then resolve. And you can see that that is going to modify the failure mode. It's searching around for the critical one, and having iterated through a few different cases, it gives me a factor of 2.14, which is higher than the original one, and we get a different failure mode. And then finally, just before we leave this example, water is obviously an issue, so simplest way to add water is to draw in a water table using this control here, and I'll just put one in sort of at this kind of level here. Sorry, click cancel by error there. Meant to click finish. Finish. So there is a water table now, and it's enabled, and then I can click solve. Having a water table there should reduce the factor of safety, so we'll let that run through, and what we should find is that it gives a small reduction in the factor, and so we get a solution of 1.44 where it's 1.77 before, so the water again has affected things, and you can move that water table around so you can experiment with different levels of water or change the geometry. So that's a very brief overview looking at a very simple slope problem. If we go back to our presentation, if we solve it with more nodes, and in that particular example we get a solution of 1.74 for that problem, so that sits pretty much in the middle of this set of results. And we can look at some other examples, so I've listed some others here. The first row here is the one we've just looked at. Another scenario where we've got the water table at the surface, and another scenario where we've added a surcharge, that's the one in this diagram, and also a horizontal seismic acceleration. And again, you can see the limit state GEO values are very similar to those from these methods for this simple slope problem where we're expecting broadly a circular type of failure. But the real power of LimitState GEO is that it can identify any type of failure mode and it's not restricted to those types. So in summary, hopefully you've seen the slip line mechanism identification is automatic. Slip line pattern can comprise of just one line or many. You don't need to worry that a critical pattern has been missed because it will hunt out the relevant one, and you can quickly and easily check the influence of modifications to the geometry or the layout. And of course, real slopes are generally much more complex than this example. They may have a complex stratigraphy, and you want to be sure you've captured the critical mechanism. So that animation there is showing a layered slope with many, many slip lines, and it's sliding on this lower stratum. So that's a brief look at a very simple case. We now move on to our second example, which is a road widening example. We've got an existing road to be widened on a slope. There's insufficient space to widen that slope. So what can we do? So one of the questions we might have, what is the current expected mode of failure, margin of safety, and can we do something such as put in a small slab Gabian solution to maintain slope stability without impinging on our take of the slope lower down the slope. So bear with me while I pull up the relevant model. So there we go. So there is our model set up. There isn't time to go through in detail all the layout, but we've got different materials, different layers of material with different strengths in this model. And I'll just run the solution to show us, just to evaluate the current stability situation. So again, we're factoring the strength of the soil to see what we've got in place. And it's telling us that we've got a factor of 1.305. And it's actually telling us we're running this now, we're using Eurocode partial factors. If I just unlock that, sorry. It's possible to pre-apply partial factors in the software according to Eurocode. So here we're applying to design approach 1 combination 2. And so you can see we're factoring loads and material properties as required. So those are pre-applied to the solution. And if I click on the solution here, you can see that these are the initial strengths of the material in the problem. These are the design values, which are effectively factored by the Eurocode parameters. And then on top of that, we have to apply this additional factor of 1.3 in order to get them down to the level at which we'd actually see a collapse. So we've got a 30% margin of safety over and above the Eurocode factor in this particular case. Now, what we want to do is widen this slope, and what I want to do is take this road base and add 3 meters to it. So I'm going to shorten that by 3 meters. And that's where I'd like my slope to be, or my road base to be, but unfortunately I haven't got the support below it. So what I can do is I can take this polygon tool again and just see what would happen if I made up that space with some made ground. So I could take a material here, drag it and drop it into the place that I want. I can modify geometry here. So what I'm going to do is click here. I'm going to set that, have a little bit of space there, 3.4, make that 0. That then tidies that up, and I'm going to change its boundary to fixed. So I've now got a widened slope. We'll just see what happens if I click solve there. So again, it looks for slope failure. Typically, because this is a frictional material we've got for this made ground, we're getting a fairly shallow translational slope effectively, translational slope failure, and it's telling us that, yeah, we're going to get a shallow slide and we've got a factor, an adequacy factor, a factor on strength of 0.9. Now that's less than 1, so that means actually the soil is too weak and it needs to get stronger. We have to divide the strength by 0.9 just to get to stability. So we're not complying with the Eurocode. That solution won't work. So we'll have a look at our alternative solution. Again, there isn't time to sort of show you how to draw that, but you hopefully got the idea of how quickly and easily we can draw in variations to the geometry. This is pre-drawn. I've now introduced some concrete blocks. So I got this width of the road where I want it to be, and again we can just click solve to see what we come up with in this case. Again, it iterates through a number of scenarios, and eventually what we get is essentially, it's a bit like a 2 or 3 wedge failure mechanism. So it's not a slip circle. It's basically translational wedges that are coming out as a critical mechanism. I can click animate just to sort of illustrate what's going on there. And as you might expect, we're getting a wedge forming behind this mini retaining wall and then sliding out. But what's important is that we've upped our factor on strength of 1.12, so that means we've got 12% extra margin of safety over and above the Eurocode. If all we need is a factor of 1, and that's showing we comply with the Eurocode, 1.12 means we've got that extra margin on top of that. Now, before we leave this example, just to show that software can capture more other failure modes. So for example, maybe unlikely, but imagine this layer here, which is modeled as a frictional material, was actually replaced with a soft clay. I can drag and drop a soft clay on that and then click solve. You can see that the software says, okay, there's a weak layer down there, we can make use of that, and the failure mechanism will therefore interact with that soft layer, and we get a very different mode of failure. So the software is able to identify the critical mechanism and take account of all changes in stratigraphy or loading and so on that might influence that, whether it's circular, translational wedges, or a combination of the two. So here we can see we've still got, it's still stable with that layer in. We've got a 10% margin of safety, so it's gone down slightly, but we've got a very different failure mechanism. And in fact, in this particular model, what we've seen is the mechanism is constrained by this boundary on the left-hand side, which is a rather artificial boundary. And we maybe would have to extend the slope geometry further out in order to see the full collapse mechanism. And we'd probably expect the adequacy or the safety factor to go down in that particular instance. Okay, so that's a very quick practical example of using the software. Hopefully you can see the various aspects of the software which allow us to explore this problem. We'll go back to the presentation now and just wrap that up. So the 2 questions we asked were, what are the current expected mode of failure? We saw that's a translational surface slide. We're getting roughly a 30% additional capacity over Eurocode requirements. If we simply widen the slope, we got a factor of 0.92, so we're 8% under Eurocode requirements. But adding that small concrete slab block does improve the mode, but we then change to a multiple wedge form. So as I've said, we could capture all the different failure modes that might occur. So hopefully you've seen the automatic application of Eurocode 7, ability to drag and drop materials, do what-if type questions, and so on. Okay, so that wraps up what I wanted to say. Hopefully I've just about kept to time. And again, hopefully you've seen weak software is ideal for identifying the critical failure mechanism for any problem geometries, loading, etc. No need to predefine any parameters, just set it off and go. And it's very easy to do what-if type analysis. So that's the presentation finished. We just have a few minutes left for some questions. So I will invite questions if there are any.
I think there was one question that came in, Colin, which is the difference between factoring loads and factoring strength.
Okay. Sorry, just picked up a question there. So there's a question about the difference between factor load and factor strength. So I didn't go through that in the presentation, but essentially for slope stability, typically you're interested in a factor of strength. How much strength can or what margin of safety do we have on the strength of the soil to cause collapse, because there's not necessarily an obvious load to address. In this particular problem, we do have a load, which is the load applied to the road, and we could ask a different question. So instead of saying, what's our margin of safety on strength, and we saw we had a 10% margin there, we could say, well, how much bigger could that load be before we collapse the soil, given its current strength? So if I click on that load there, I've just set that load to be a variable load. So these are Eurocode designations with a normal stress of 10, and it's an unfavorable load. And if I flip this setting up here to factor load, then I can say to the software, how much bigger does this load up here have to be to cause collapse? So I click solve. I'll get a slightly different failure mechanism. In fact, I've still got the soft clay in there. And what it's telling me is I've got a factor of 2.64. So if I click on that, it's saying, well, we started with a value of 10. Eurocode partial factors would make that variable unfavorable load 13. But actually, to get failure, you're going to have to multiply that by an additional 2.6. So you require a load of 34 to cause that system to fail. And what you often find is the margin of safety on the factor you get on a factor and load calculation is typically higher than that on a strength calculation, because in this particular case, we're just asking the software to tell us how much bigger that load there itself has to be, and not the weight of the soil around that. But if we reduce the strength of the soil, it's still got to carry the same weight of that soil that forms the slope. And we can ask the software, we can ask it to tell us how much more we have to increase several loads by. We don't have to stick to one. We can pick several loads and say, well, tell me in combination how much we have to increase that magnitude of load by. But it basically gives you a way of asking the software two questions. Factor and strength is a typical one you want for slopes, but if you're doing a bearing capacity, you might be more interested in how much extra load can I apply to my foundation before it collapses. And here I've just changed this layer back to a stronger frictional material, so we're back to this kind of wedge solution. It's changed slightly because we're now saying how much bigger does this load have to be here. We're getting a value of 3.6. But we're still getting this kind of multi-wedge type failure up at this end of the slope. Okay, so that's hopefully answered that question. Probably we're running slightly over time now. Tom?
Thanks, Colin, and thanks to everybody for listening today. We've now reached the end of the webinar. We do hope that you found it interesting. A recording of the session will be uploaded to our YouTube channel in the next day or so, and we'll also send out notifications by email when this is available for you to watch. The webinar was the first in a number that will be dealing with LimitState GEO and its application to particular problem types, so do please look out for the notifications of that, which will be sent out via email and posted on our website and social media. Finally, just like to say thank you again for listening, and hope that you can join us again for one of our future sessions. Goodbye.